Okay, so using the information we have, y is 100 centimeters. This says that if y is in centimeters, dy dt will be in centimeters per second. So, in centimeters, y is 100, so that's what I put in the square root. I don't put in the centimeters because y is understood to be in centimeters. And now dy dt has to be in centimeters per second. So we have to understand what everything means, which means that we have to use all the information we have if we possibly can. It doesn't mean that in a given situation, you'll always use every bit of information that's there. Okay? Often there's information that's not even relevant that you got to discard, but you got to consider every bit of information and make sure you're using everything that's relevant, right? Just a general thing you have to do when you read a problem, think about a problem, or when you encounter a situation in a real world or in the lab. Okay? Okay, so anyhow, we got this, and it's in centimeters per second. Okay? So now, if that continues for the next, and of course that equals -1 centimeter per second, right? Okay? Now what's the premise? This continues for 10 seconds, right?
Yeah.
So what's your conclusion?
It'll be 90 centimeters.
so stay right
No, that's not your conclusion, but that's right after the conclusion. What's your immediate conclusion? Don't skip steps.
Multiply that by how many seconds?
Yeah, well, your immediate conclusion is it'll go down 10 centimeters, right?
Yeah.
But to get that conclusion, do exactly what you just said. So, obviously, then, in 10 seconds, at this rate, depth y going to change by -10 centimeters. Meaning water level go down 10 centimeters, right? Now we want to be a little bit more careful than just say obviously, right? Formally, rate of change of depth with respect to, WRT stands for with respect to, okay? I don't want to keep writing out those words. I mean, I don't mind, but it takes up time. So rate of change of depth with respect to clock time is rate equals change in depth divided by change in clock time. And what symbol do we use for a change in something? Delta, right? So that's delta y, depth being y, we're going to call that delta y divided by delta t. And incidentally, on the homework, most people did a real good job with slopes. And people already mentioned that slopes and rates are the same thing if you're in the right context. So if we had a graph of y versus t, a graph of depth versus clock time, and you know what that graph looks like, this would just be the slope of your graph between 2 points, right? Well, more about that later, but you have that idea. Okay? Now, knowing that, it follows immediately from this that the change in depth, well, you multiply both sides of rate equals delta y over delta t by delta t, and you find that the change in depth, the delta y, is the rate times delta t, right? Now I'm leaving out an important word, and I left it out so I could emphasize it rather than just writing it down. This is actually an average rate, because there's a difference between an average and an instantaneous rate. And you have to be sure you know which one you're using, otherwise you're going to be prone to some error. So I better put the word average in here too. Average rate times delta t, right? Now, this -1 centimeter per second we're taking to be an average rate. It's also an instantaneous rate. It's the instantaneous rate when the depth is 100, right? Okay? And we're assuming that that's going to be the average rate for the next 10 seconds. Is that really going to be the case? What happens to the rate at which water descends, the rate at which depth changes in this situation? It decreases, doesn't it? Mm-hmm. Okay? So that assuming that the rate stays at -1 centimeter per second for 10 seconds, it really doesn't. It's just an approximating assumption, right? That makes sense? Mm-hmm. So we're going to be off a little bit if we use this assumption. Well, the kind of model that we're doing, it's a finite element model, and you always have uncertainties. Okay? And, you know, there are always error estimates. Not error estimates, there are always calculation errors based on the assumption that the rate stays the same for a while. Okay? There are ways to get around that. For example, you can say, okay, well, we think that's going to be 90 centimeters, but we know it's really not going to be. If it was 90 centimeters, then the rate would be -0.9 centimeters per second. So let's average the two, go back and recalculate, and find out that we only go down 9.5 centimeters. Now, if you understood that, fine. If not, it's okay. Right now, if you just understand this, it's great. Okay?